Okay, so now we want to get into section 4.1. So this is going to move us into our finance section of the class. And the first thing we want to talk about in 4.1 is exponential functions. They're things you've seen before, but maybe didn't realize it, or maybe you've forgotten. So we'll talk about some properties of exponential functions. We'll talk about the difference in linear and exponential growth, and then we'll visualize. Meaning we'll look at kind of what exponential functions look like from a graphing standpoint. So the first thing, just as a recap, and we talked about this in the first 3 chapters of the test, or first 3 chapters of the class, what it means to be linear. Okay, so to be linear, all that has to happen is we have to have a constant slope. Okay. So we're just going up by the same thing every time. So the linear model is this middle column, and as you can see, these all have a difference of 4,000. Okay. All right. So to be exponential, that means we have what we would call a constant growth factor. Okay. And really could just say a constant factor to generalize. So what that means is each new step, so say here for the first example, 24,000, divided by the previous step of 20,000 will be equal to the next step of 28,790 divided by 24,000. And then that will be equal to 34,540 divided by 28,790. So instead of going up by addition or subtraction, we're going up by a multiplication or a division, okay? Or decreasing on that manner too. All right. So how can we look at an exponential and know if it's linear or if it is an exponential? So linear, again, as I mentioned, always has a constant slope, so it's always going to create a line, a straight line. An exponential is always going to have this kind of curve. Okay, so as in this case, we have exponential growth. So as x gets bigger, our y gets bigger faster, right? So just as, to think of an example of an exponential, let's say rabbits. And this is just just as an example, or if you wanted to start a rumor, right, so to speak. All right, so you tell 2 people, 2 people tells 4 people, right? 4 then turns into 8, 8 turns into 16, 16 turns into 32, 64, 128, and so on, right? So that's how an exponential works. Two rabbits turn into 4. 4 rabbits then go to 8. 8 to 16, and so on. Okay, so as we get bigger, our gaps are going to get larger because we're multiplying as opposed to adding or subtracting. Okay. All right, so our generic form of exponential growth and decay comes in this form: y is equal to CA to the positive, or CA to the x, the power of x. C represents our initial value, so it's our starting population. So 2 rabbits, or even if it's just ourselves, starting a rumor, right? So you have to have a starting population. One thing about that initial value is we're always going to be positive. Okay, for the context of this class, most of the time we're going to talk about money or populations. So the initial value, you always have to start with some kind of money, right? To grow any interest, you have to start with some kind of population to then have reproduction in that population. All right. Then A represents our growth and decay factor. Okay, so how we know if it's growth or decay, we have stipulation here. So if A is greater than 1, we have growth. Okay. So because we're multiplying by something larger than 1, we're going to continuously get bigger. All right. If A is between 0 and 1, so notice A will not be negative. A is between 0 and 1. Then we have decay, because we're essentially dividing at each step as opposed to multiplying. All right. And then the independent variable will be x. We'll change that in and out. It could be t a lot because we'll talk about functions of time, but we'll get into that in 4.2. Okay, so here's an example. So without graphing, I'm not terribly particular on this. If you want to graph it to look at it, great. But this is just off the homework, so I just wanted to talk about it. So without graphing, answer the following questions for the functions below. So we want to describe the shape of the graph. So do we have growth or decay? Okay. So for this first one, y is equal to 2x. Our a value, a is whatever is being raised to the power. So a is 2, which of course is greater than 1. So we have growth. Okay. Now find the second coordinates with the first coordinate 0 and 1. What that means is we know, and here because I don't have an initial value, my initial value is 1. So what that's saying is with the first coordinates 0 and 1, that means when x is 1, or x is 0, y is 1. Okay, so I have an initial value of 1 is what this is implying. So to find the second coordinates, we're just going to simply plug in x is equal to 1 and just figure out what the value of y is. Here we have 2 to the first power, so it's simply 2. Okay. For our second example here, we have 4 to the negative x. Okay. One thing to remember about the powers of negative exponents, right? So if we have something, this was our power rule that we referred to in our exponent section. So if we have something to the negative power, that's the same thing as saying dividing it by whatever the x value is, for our generic form, raised to that power. Okay. Something to note here, however, so we know that this is actually y is equal to 1 over 4 to the x. Okay. So my a value is less than 1 and it's greater than 0. So we're going to have decay, but I do want to remind you of this. Okay. So if I have 1 in the denominator, in the numerator, then I can say this is actually 1 over 4 to the raised to the whole quantity raised to the x power. And the reason that's significant is now we can clearly see our a value is between 0 and 1 because it's 1/4. We could see that in the previous step, but now we can clearly denote a is 1/4. Okay, and the reason that works that way is because 1 raised to any power will always be 1, so that won't affect the numerator in any capacity. Okay, so a is equal to 1/4, and 1/4 is between 0 and 1. So it's less than 1, and just, I'll say over here it's greater than 0. So we have decay. All right. Similar to the first coordinates and second coordinates, I have x is equal to 0, y is equal to 1. Even though it's a fraction, anything to the 0 power is 1, with the exception of 0 itself. All right. So then when x is equal to 1, then y is equal to just 1/4. Because I plug in 1 for x, I get 1/4 to the first, that's 1/4. Okay. All right, so something that we're going to use more so, well, I won't guarantee more so, but I'm going to say a lot, is continuous growth and decay, and it has its place in finance, and we'll talk about it. But in our generic form of the y is equal ca to the x, we are limited on our time intervals because we can only plug in, it would be referred to as a discrete. So no matter what time intervals you plug in, 1, 2, 3, 4, so on, there's always a gap. So even if I went 1.1, 1.2, there's still a gap between those. So it grows a little bit slower than that of a continuous, because a continuous function, like with compounding interest, is nonstop, an infinite amount of times continuously compounding. Okay, and to show that, we use Euler's number. Okay, Euler's number is just represented by the letter E. Euler's number is approximately 2.71. You can plug it in the calculator as E on Desmos, or if you use your TI calculator, you can. It is a second, and then the power, or the caret, I think, is the function button for that. But it's just a number, and it's just represented like by E, similar to pi. Okay. C represents the initial value, so nothing changes there. E to the k represents the growth or decay factor, so you can kind of think of E to the k as being equal to A. All right, and our stipulation to be able to look at it without evaluating E to the k is if k is positive, then we're going to have growth. If k is negative, we're going to have decay. Okay. All right, so k is positive, we have growth. K is negative, we have decay. All right. So just to look at two examples of this. So my k value for the first one is 1.2, okay, which is greater than 0. So I have growth. Okay. To find that first and second coordinate stuff, we're going to do the same thing. So x is equal to 0. When that happens, y is 1. When x is equal to 1, then I'm going to just plug in 1 for x. So I get e to the 1.2 times 1, which is just itself 1.2. And that is approximately 3.3. Okay. All right. So that is approximately 3.3. All right. And so then for our second example here, we have k is equal to negative 0.29, which is negative, and so it's less than 0, so we have decay. All right, so then when x is equal to 0, y is equal to 1. Still, that's good for us. When x is equal to 1, y is equal to e to the negative 0.29. And plugging that in the calculator, that approximates to 0.75. So that solidifies that we had decay because we got smaller. And e to the negative 0.29 is less than 1. So therefore, our a value, right, that would solidify decay. All right, so that is it for the basis of exponential growth and decay. So for 4.2, we'll talk about applications. But let me know if you have any questions. And as always, feel free to reach out and email me, and have a great rest of your day.